when you buy a linear guide, and I'm drawing, this is the rail, and then around that would have been some sort of block, right? And then you would have maybe 1, 2, 3, 4 rows of ball bearings. And just as a if I 3D, it might look like this. It might be a little bit better if I drew it like that. Okay, get the idea. And then up here you had the mounting holes where you're going to mount something. There you go. So let's say that you had this linear guide, and you go to mount it. This isn't part of your assignment, is to figure out how to mount it. But one of the things that you would have to do in the real world is figure out how to make this, line up. And I almost shouldn't have drawn it 3D, because if you actually look at how this is supposed to be done, there needs to be some sort of surface, and that surface always has something like this, right? Where right here, that is your datum. And if you actually read the mechanics manufacturers on, because remember, they only sell this bearing in terms of relative straightness. So how closely does the bearing block follow collinear to the rail? And so they say, hey, yeah, the block follows the rail, and it doesn't go back and forth like this a whole lot. It follows, and they call this term the running, I think I talked about this, running parallelism. Okay, they can't really list an accuracy because they don't know what you're going to mount it to. They don't know what, if you have some big heavy piece of steel down here, or worse, if you did something and you just mounted it to a piece of 1/8 aluminum. So they can't really tell you until, but all they can do is tell you what's the relative parallelism between where the block's going to go and where the rail's going to go. And then what they do is they say, when you go to mount this thing up, you actually physically would, let's see if I can draw this, you would physically put a C-clamp in here and squeeze this together. You'd squeeze this, and you'd squeeze this right here over to that datum. And you would do this at each bolt hole. You'd squeeze it over with a C-clamp or some type of clamp, and then you would go ahead and screw it down. Drive the screw in and tighten the screw. So there's an actual process of getting one of these bearings mounted, which means that the hard part of all of this isn't the procedure. The hard part of all of this is you have to have, I'll just draw it a little bigger. You have to have that. You have to have the ledge, and it's machined. You have to have a machined edge to squeeze this up against, and it's machined straight to the tolerance you want. That's where you get your straightness. It's kind of important for you guys to understand that you don't just buy these bearings and just bolt them down. There's got to be that datum. So one of the questions that comes up, and it's come up twice in a row now, is something that as you're designing along, you're probably going to have to deal with a little bit, and that is the difference between travel length or stroke that you need for your motion and overall length that you need to support your bearings. What I mean by that is, let's say that you have this x-axis not drawn flat, and you have some you have a little carriage here that you're moving back and forth with the ball screw or belt drive or whatever, right? So we know that what gets mounted on this is some tall structure that has a y-axis, and then it has some concrete extruder out of it, right? So it's this big structure out there. It has some mass to it, and it gets mounted on this. And then, so there's some center of mass up here. I don't know where it is, and it actually changes depending on, as this goes up and down, that center of mass moves up and down. So you might be looking at the worst case is kind of up here at some point. And then you're going to do a terrible thing. You're going to accelerate it. And so now you have a force due to the mass and acceleration creating some sort of moment on this bearing. And when you draw it out, it's like, oh, wait. And this is about how I actually expect your drawing your sketches as you're doing this part of the design. This is about how they should kind of look if this is the situation. It doesn't need to be any greater than this. And then a couple of dimensions here and there, and you kind of got it, and you say, oh, this is going to be a pitch moment on that particular bearing in this configuration. Okay, so then you go choose your bearing, and you choose you're choosing actually two separate things. One is you're choosing something to do the motion part of it, the translation. You're doing the translation part. And that is belt drive, rack and pinion, ball screw, motors, controls, amps, all that stuff. And then the other thing you're choosing is the bearing and support structure. This is particularly, in this case, you're looking at the loading that is going to be going on it and deflection.
This is like our stage for this case, right?
Yeah. Yeah. Now, this is for the real machine. This is your design project, not necessarily the one that's on your desk. The one that's on your desk is just a shrunk down version for you to do proof of concept programming and motion control and show that, if you did buy the big one, this little, see, look, I could do it. It just scales up. So then you would go look up and you'd say, okay, well, what's the pitch moment? Well, generally you're going to find out that, ooh, this motion control device has lots of force this way, and it can probably handle lots of force this way due to gravity. But that doesn't mean that they built a bearing that can handle the pitch moment that you're putting on it with your load. So what do? It may be that you run a separate bearing. Sometimes you might do this. Sometimes you might go to the manufacturer and say, hey, I'd like to buy a special version of this. And the special version has this one and this one. And then what you do is, you know what, let's put a plate across these two and then attach this to the plate. And now what happens is all of a sudden, instead of a moment load being put on this bearing on a single unit, which is how they would sell it, that'd be that's what they would sell, because they're selling something that moves back and forth. If you want bearings, you got to go buy bearings. But you could buy bearings, in this. But the thing, as soon as two things happen, first is all of a sudden now this bearing here shows the force now. Let's say you are accelerating it this direction. Uh-oh, what happened here? There we go. You're accelerating it. Give me my pen, come on. That direction. That would cause a force there and a force there. So instead of a moment about a small point here, that is very limited because you'd be squishing balls those would be highly compressed and these would not be compressed. Instead, when you expand it, it spreads the load out over all these little balls that are in here. And essentially you don't look up the pitch moment of that particular bearing anymore. You look up the load in this direction that it can handle and the load in this direction that it can handle. And it's spreading it out over all the ball bearings, and it's going to handle it. It's going to be a lot easier. The trouble is, this is the difference between you're designing you're asking what we just did is ask the translation device to do load support, which maybe it can, but in general, probably what you do is do a separate bearing structure, let the motion control part move it back and forth, and design a separate bearing structure to do that, in which you would select a rail and a couple of bearing blocks. Okay, but the one other thing to pay attention to here is when you bought this device here, this translation device, you had essentially, let's see, you had a limit switch here and you had a limit switch here, and that distance minus this distance, the width of this block right here, was your stroke. Because this would move down here, and you'd have this, and really, so you had that much, so you had some things subtracting from the available stroke. And then as soon as you added outboard bearings, your overall envelope of the machine got larger. But if you did this in the translation stage, then essentially you had to put in a whole bunch more rack to accommodate the fact that you were just trying to spread the bearings apart. And so that's where you say, you know what, I don't want to buy a huge motion system. The ball screw got longer, the inertia went up, the belt was longer, all that's bad. You want to just buy the stroke that you need out of the motion device, and then buy separate bearings depending on how you need to support the load. So that would be the proper way to design this, but you have to separate in your mind the stroke that you need from the overall distance and the room that the machine's going to take up. And the room that the machine takes up is always quite a bit larger, especially as you try to support the load properly.